It's a pleasure to be here, talking to all of you. I'm really sorry that I was out of town last week. I was in Aspen and had to miss the more, full first week of the workshop. But I guess this week we're going for quantity over quality, or quality over quantity. Okay, so in that spirit, I'm especially honored to be talking this week. Let me just say as a word, as sort of a preliminary word, I'm not a condensed matter theorist. I am much more of a field theorist and someone who works on the gravity side of things, the ADS CFT side of things. I'm going to try and use as much as possible a sort of common language of conformal field theory that will hopefully be kind of broadly intelligible. But I very much encourage everyone to stop me, interrupt, ask questions. If anything requires clarification, or if there's anything that you'd like me to follow up on in a little bit more detail. And of course, I'm going to try and keep things sort of relatively broad, and only maybe get into a couple of the more technical details at the very end if we have time. But I'll keep things as sort of broad as I can. So let me just start with a little bit of an overview. Conformal field theories are really the building blocks of quantum field theories. For me as a field theorist, I really think of them as fixed points of renormalization group flow, and they describe theories with no dimension full scale. Okay, so for example, one of my favorite examples of a CFT would be that which describes the Ising model at its critical point. So for example, the Ising model, of course, is a system of interacting spins. It typically has some sort of correlation length, the typical length scale at which these spins are correlated. And then if you tune to a critical point, say by going to some critical value of the temperature, this correlation length will diverge. And instead, we would describe it by a continuum system rather than a discrete system with some spins living at lattice sites. And because the correlation length has gone off to infinity, this is a theory with no dimensionful scale, and it's a theory of local degrees of freedom. So we describe it using a conformal field theory. And in particular, we would describe it with some sort of local operators, along with some interactions between those operators. In the case of the Ising model, the description of the local operators is rather simple. I've listed three of the local operators here, the sort of three most important ones. There's what we might call the identity operator, the operator that does nothing. There's a spin operator, which measures the spin at some site. And there would be some energy operator, which measures the energy density at some site, which morally speaking, because it's the Ising model, you can think of it as being something like something quadratic in the spin sigma. And in general, there will be other sorts of local operators that you could build out of these things in this very simple conformal field theory. So in order to talk about CFTs a little bit more generally, let's think, and let me remind you of what the data is that defines a conformal field theory. So here I'm going to be focusing on conformal field theories in two dimensions. And the data that defines a conformal field theory is first a spectrum, and then a set of coupling constants. So in the case of a two-dimensional conformal field theory, the spectrum would be defined by a list of scaling dimensions and spins for all of the operators in the theory. So here I've labeled my operators OI. I is some index that labels the different primary operators in the theory. And then I need to specify their dimensions and spins, which I usually write in terms of a left and a right moving spin that I call H and H bar. Okay. Good. H bar is not that H bar. Coupling constants in a conformal field theory are described in terms of what we call the OPE coefficients. So in particular, if I have two of these local operators, OI and OJ at different points, then I can expand them in a basis of local operators. And the expansion coefficients are roughly the 3-point interaction coefficients in the theory. And these are the things that we call CIJK, the OPE coefficients. And then there are some powers of X that just make up the scaling dimensions, because these OKs will have different scaling dimensions than OJs and than OI and OJ. So this is the basic data that defines a conformal field theory. a list of scaling dimensions, h and h bar, and a list of operator product expansion coefficients. And once you've specified that data, you've completely specified a conformal field theory. Yes. Good. So I wouldn't. So the central charge is also something that appears when we study two-dimensional conformal field theories. I wouldn't necessarily think of it as something different, but we could include the central charge here if we like. So basically, the central charge for a 2D CFT is a dimensionless number that, roughly speaking, characterizes the number of degrees of freedom in the system. I think about it as an anomaly coefficient that describes how the theory behaves when we introduce a length scale. So, for example, if you put the theory on a circle, then it'll have a Casimir energy, and the central charge is that Casimir energy. Or you can describe it in terms of correlation functions of the stress tensor, or in terms of the high energy density of states, or any one of a number of ways. Yeah, well, yeah, strictly speaking, I used the word primary operator here. The stress tensor is a quasi-primary, not a primary. So strictly speaking, it's not an OPE coefficient. Yeah, exactly. So so when I use the word, just to make sure we're being completely precise here, the idea is that these two-dimensional conformal field theories have a huge amount of symmetry. And when I talk about primary operators, what I really mean is I'm organizing in representations of that symmetry group, okay? And so the primary operators are like the highest weight representation. I'm labeling, they're the highest weight states under the symmetry group, under the symmetries of the theory. And so you should really think, when I talk about primary operators, I'm talking about the number of representations of the conformal symmetry group that are appearing in this theory. And in 2D CFTs, I think of the central charge as a parameter that labels the symmetry group, if you like. It's a parameter appearing in the Virasoro algebra. Good. Please, any other questions? Yeah.
So this talk will matter whether you're Euclidean or Lorentzian?
Yes. Yeah. So I will be going back and forth between Euclidean and Lorentzian signature. And I'll try and use the right words to signal exactly what I mean when I do so. So the basic story, though, and we can get into as much detail as you like, but the basic story is that, unlike in more complicated quantum field theories, when we live in CFT land, I know exactly what the data is that defines a conformal field theory. It is this data, a spectrum and a list of OPE coefficients. That's it. If you know that, you could compute everything else in the theory, at least in principle. It's just a matter of working hard enough. And moreover, we know exactly what the constraints are that this data satisfies. So in particular, it obeys what are known as the conformal bootstrap constraints, which are really just another way of saying that these data, the spectrum and the OPE coefficients, are subject to the constraints of unitarity and conformal invariance. And when we impose the constraints of conformal invariance, we usually do that using what's known as crossing symmetry. So what is crossing symmetry? Crossing symmetry is very simple. It's just the idea that you take a correlation function in your conformal field theory. So here I've written down a 4-point function. And it's just the statement that if I wanted to evaluate this 4-point function by using this operator product expansion, there are two different ways I could do that. I could take these first two operators and expand them in a local basis, and the second two operators and expand them on a local basis. And that would represent this 4-point function as a sum over intermediate states, where I take x1 with x2, x3 with x4 in terms of some intermediate state. Or I could expand it in a different way, where I would take x1 with x4, say, and x2 with x3, as I've done here. And the statement of crossing invariance is just that you have to get the same answer no matter which way you do this. Okay? About it. This is a constraint on these OPE coefficients, because every time you use this OPE, you get a factor of these OPE coefficients. So this is some quadratic constraint on the OPE coefficients. And the name of the game, if you wanted to try and classify conformal field theories, is to solve these constraints. And in some cases, this is actually possible. So for example, I presented the 2D Ising model earlier, and that's a case where you can actually completely solve these constraints. It turns out that if you organize everything into representations of the symmetries of the theory, there are only a finite number of representations. It turns out there are 3 representations. The central charge is equal to 1/2. And you can find the spectrum of the theory. That's the spectrum of operator dimensions. And you can find the OPE coefficients. Okay, and that's it. That's the solution of this particular 2-dimensional conformal field theory. The problem, however, is that this 2D Ising example is extraordinarily special. It's an example of what we would think of as an integrable theory, one where we can solve these constraints, these conformal bootstrap constraints explicitly. And this, it turns out, is an extraordinarily rare and special occurrence that only happens at relatively small values of the central charge. And in the generic case, it's impossible to solve these conformal bootstrap constraints exactly, although I would love to be proven wrong. I think that's a true statement. Yeah, Yona.
Can you say more about what's special about like the rational?
Absolutely. There's many different ways of thinking about it. The way that I think about it is that, well, first of all, there's a big difference between 2-dimensional conformal field theories and higher dimensional conformal field theories. In conformal field theories of greater than 2 dimensions, the symmetry group that you have is some finite dimensional group of symmetries. In 2 dimensions, this gets enhanced to this infinite dimensional algebra of symmetries. And so because you have an infinite dimensional algebra of symmetries, it's at least in principle possible that all of the states in the theory, all of the operators could be organized into a finite number of representations of that symmetry. So in the case of D = 2, this gets enhanced to a Virasoro symmetry, actually 2 copies of a Virasoro symmetry. This is an infinite symmetry algebra. And, if you have a theory with local degrees of freedom, it, morally speaking, has an infinite number of degrees of freedom. And so you could never organize an infinite number of degrees of freedom into a finite number of representations of a finite group. But it is possible to organize an infinite number of degrees of freedom into a finite number of representations of an infinite group. And so, we're comparing infinities to infinities here. And so the real question is, under what circumstances can we take the infinite number of degrees of freedom in a local field theory and organize it into a finite number of representations of this infinite group? And it turns out, and there's a couple different ways of understanding this, that it only happens when the central charge is less than 1. Okay. So it turns out that this central charge is the crucial parameter that lets you decide whether the infinity that measures the number of degrees of freedom in the theory is bigger or less than the infinity that measures, the size of the representations of this group. So it turns out that when C is less than 1, you organize into a finite number of representations of this group. And when C is bigger than 1, you have an infinite number of representations.
Sorry to correct.
Yeah.
If you have an enhancement of the Virasoro symmetry by some other symmetry, then you can have a
Absolutely.
number of representation of the symmetry.
Yeah. That's
Rational theory with bigger value or C bigger than 1.
Yeah.
Example,
So
S2.
yeah. So the reason why I said small values rather than C = 1 was because I was thinking in my head about cases where you have enhanced symmetry. So for example, if you have supersymmetry, or if you have some enhanced W algebra or something like that, then you can have theories that are rational with respect to that larger symmetry algebra that have C bigger than 1. Absolutely. Yeah. So that was, that's why I said relatively small values rather than C = 1. Absolutely. Good. Great. Any other questions?
Good. So when you said that you can solve these bootstrap equations for the Ising model, what do you put in to tell me that it's the Ising model? Because that's what you're trying to get out, right? So
good. So what I really put in, so I think the best way of thinking about it is if you start with a central charge, then the number of possible unitary representations of the Virasoro algebra is finite, and then it's a finite mathematical game to construct a consistent CFT out of those finite number of representations.
I guess I'm in
I really think of the central charge as part of my parameter that defines the theory. Yeah. So good. Yeah. I mean, maybe what I would say is let's not get into too much detail about the classification of rational CFTs, since in some ways my interest is in the exact opposite thing in this talk. Okay. I mean, I will say though that, you know, morally speaking, I think of CFTs with C less than 1 as much closer to theories of quantum mechanics than to quantum field theories, because, you know, quantum mechanics is the setting in which we have a finite number of representations of some symmetry group. And it's really the theories with C bigger than 1 in the Virasoro case, or C bigger than the number of currents in the case with some extended symmetry algebra, that are the analog of higher dimensional, that are sort of more more analogous to the higher dimensional quantum field theories, where we would have real infinite numbers of representations. These would generically be chaotic theories as opposed to integrable theories. Of course, we need to be precise about exactly what we mean by chaos in that setting. But really, you know, if you're interested in things that are the analog of higher dimensional theories, things like the 3D Ising model or other more interesting interacting theories, we're really in the land not where C is less than 1, but where C is bigger than 1. Yeah, please.
Regarding the Bootstrap equation.
Mhm.
Equation is not really a good name. I would say consistency condition.
Sure.
Because
Yeah.
you start from scratch, you don't even know which variable you have to use to fit into the equation. So
Yeah.
it's not an equation that you can solve. It's an equation that you have to start from some data and then try to consistency code, but you don't know a priori which are these data. And so it's just a very loose set of consistency conditions.
I mean,
so equation is maybe too much of
well,
a word, because you cannot strictly solve them unless you put something in.
Sure. Yeah, you need to start by defining, for example, you know, the setting in which you're working in order to find a solution. I mean, let me give you an analogy that, you know, this is a math research institute, so let me give you a math analogy that I think might be helpful. Let's talk about a 2D CFT where you're talking about spin 1 currents. So these are operators with h equal to 1 and h bar equal to 0. Okay, they have some some OPE coefficients among themselves, and then this is some quadratic constraint among those OPE coefficients. And it turns out that those OPE coefficients are the Jacobi identity. And mathematicians, you know, we all know what the classification of the solutions of the Jacobi identity are. It's the classification of Lie algebras, right? And so the classification of Lie algebras is an example of the solution of a kind of crossing symmetry, a kind of bootstrap problem in a very simplified setting. The thing that's special about that case is that all of these OPE coefficients kind of close among themselves if you're talking about spin 1 operators. So you get a closed system of equations where you're trying to solve for a finite number of unknowns using a finite number of equations. The thing that's really difficult about the conformal bootstrap problem is that it's a more complicated problem that includes, for example, the classification of Lie algebras, but it involves operators of all dimensions, okay, rather than just those of dimension 1. And so I think about this as some infinite analog of the problem of classifying Lie algebras. So that's maybe a mathematical analogy that would be a little familiar to some people. So my interest is not in trying to find explicit solutions when C is less than 1. Instead, I'm interested in cases that are more analogous to higher dimensional quantum field theories where C is bigger than 1. We have an infinite number of representations. And in this case, it's more or less impossible to find explicit solutions. However, what we will discover is that it's possible to find an averaged solution of crossing symmetry, an averaged solution of the bootstrap conditions in the following sense. So this will be an ensemble of data. That is to say, it'll be a probability distribution over the space of data that defines a conformal field theory. Okay. So the data that defines a conformal field theory is a spectrum and a set of coupling constants. What we'll find is that if I treat these data as random variables, rather than as, sort of specific variables. That is to say, I consider some probability distribution over the space of variables. Then you can find an averaged solution of these bootstrap conditions. And this is very much what we do in physics when we study systems with quenched disorder. Okay, you study systems where the coupling constants of the theory or the Hamiltonian of the theory is viewed as a random variable. So the sort of example that you might be most familiar with is the case of quantum mechanics, where you think of your Hamiltonian not as a specific n by n Hermitian matrix, but rather as a random matrix pulled from some ensemble. Okay, so the simplest example would be, say, a Gaussian unitary ensemble, where essentially the components of the Hamiltonian are Gaussian random variables. And then, one can solve this theory exactly. You get the Wigner semicircle eigenvalue distribution. So that would be the analog of this continuous spectrum that I'm describing here. And so what I'm talking about really is a quantum field theory or conformal field theory analog of random matrix theory. Also, those of you who are condensed matter theorists studying disordered systems, you might be quite used to the idea that the coupling constants appearing in your Hamiltonian would be random variables, stochastic variables pulled from some distribution. And so what we'll discover is that there is, although we can't find an individual solution of these conformal bootstrap equations at large C, we can define an ensemble solution, a probability distribution over the space of CFT data, which I think of as a maximum entropy probability distribution on this data subject to these bootstrap constraints. Yeah, there's a question.
Maybe this question is jumping ahead, but
Mhm.
so I'm curious about, so when we do sort of random matrix theory in the context of Hamiltonians,
Mhm.
we know that, in fact, if you look at an individual Hamiltonian, which need not be disordered,
Yeah.
we can learn a lot by looking at this,
Yeah.
on the properties of the ensemble in particular, when we look at, finite temperature, eigenstates, so finite energy density, then, a lot of stuff basically looks like it does in this random ensemble. So I just, physically, what does an ensemble of CFT?
Good. I mean, the way that I think about it is that, I think about it, here's the way that I think about it. Okay, so if we're talking about quantum mechanics, then the sort of the analog of the bootstrap constraints are just the statement that my Hamiltonian is a Hermitian matrix. Every Hermitian matrix defines a good quantum mechanical theory. And so there's no particular difficulty with, quote unquote, solving the bootstrap constraints and then averaging over the set of constraints, and then if we wanted to averaging over some space of Hamiltonians. The problem is that when we talk about higher dimensional quantum field theories, not just quantum mechanics, solving the bootstrap is a much more difficult thing to do. And so one thing that is, one sort of feature that I would advertise is that although it's very difficult to solve these constraints in individual conformal field theories, it's much easier to solve them in average. I can more or less write down completely explicit formulas for everything that I might want to study if I study these on average.
But I guess the question is an individual CFT requires
the way,
sort of
good. That's exactly right. Yeah. Okay. So the next thing I was going to invoke was the idea of chaos, right? Because the idea, so the way that I think about it is the following. So let's imagine that I was studying a spin glass. Okay, what is a spin glass? A spin glass is a chunk of material with a Hamiltonian and a Hilbert space, but one that's very, very difficult to describe. And instead, what we do is instead of treating the coupling constants of this material as essentially random, we treat them as actual random variables. And so when I study a spin glass treating the coupling constants as random variables, I'm literally studying an ensemble of Hamiltonians, right? And the point is that this ensemble is often much easier to study than any individual instance of the ensemble. And usually so you might be very worried about that. But the important point is that in systems that are sufficiently chaotic, you use the word self-averaging, this ensemble averaging is more or less harmless, right? It washes out small scale structure, but it keeps large scale structure. Okay. And that's essentially how I think about this ensemble. If the individual elements of this ensemble are chaotic conformal field theories, then the effect of doing this ensemble averaging is to wash out microscopic structure. So, for example, you won't have a discrete spectrum, okay, which is what you expect, right? It'll wash out the structure that is, like the level spacings will be of order e to the minus s, where s is the entropy of the theory. It'll wash out that microscopic structure, but it'll preserve a lot of this sort of larger structure that appears in the theory. And one of the things that's surprising is just how much structure is preserved. One of the things that was surprising to me, at least. Was there a question or yeah?
It's a little bit part of the topic, but now you understand theory of simulation. You say that without an ensemble of Hamiltonians, every time you start with a Hamiltonian, we'll flow to one fixed point somehow.
Mm-hmm.
And what you're telling me is the probability of which I will get to this fixed point given the initial condition.
I'm not thinking about renormalization group flow necessarily. Well, one way of thinking about conformal field theories. So good. Well, it may well be the case that different UV completions would lead to different infrared conformal field theories that you flow to in at low energy. What I wouldn't want to say is that the probability distribution that I'm going to describe here is the probability distribution that you would get through some, studying the space of renormalization group flows like this. I'll describe it. So I have a different motivation for writing down the sort of ensemble that I'll discuss. I mean, in order to define an ensemble in the way that I think you were getting at with your question by looking at spaces of RG flows, I would need to start by defining a probability distribution on the space of UV couplings. And that seems like, quantum field theorists do this all the time anytime anyone uses the word naturalness in quantum field theory, implicitly that's what they're doing. I'm going to take a slightly different approach because I've always thought that's a little ad hoc. And so I'm going to take a slightly different approach. Great. Please, more questions. This is great. Good. Okay. So I'm going to write down an average solution to the conformal bootstrap, which is some probability distribution on the space of CFT data. It turns out that this is a solution of the bootstrap at large C, but it will have corrections that are going to go like e to the minus C. So it will only be a solution at large central charge, and not, for example, describe things like the rational CFTs at small values of the central charge. But it turns out that my primary interest as someone who studies gravity is that this ensemble has a remarkable interpretation. It's general relativity. Yes.
So in this ensemble, you're not averaging over C itself.
No.
It doesn't matter.
We could talk. Yeah, we could talk. Yes, you could average over C. To some extent, whether we fix C or some other parameter, I don't know, chemical potential conjugate to C or something like that, doesn't really matter. But yeah.
Like subleading corrections.
Yeah. We can talk about subleading corrections. I'm going to make a statement that I actually believe is, I think that, in terms of explicit calculations, we'll be working at large C. I think I'll be able to make statements that are true at all orders in perturbation theory on 1 over C. That's my conjecture, but I would have to be a little bit less explicit. Okay. So my claim is that the ensemble that I'll write down is Einstein gravity. Okay. It's Einstein gravity in a universe in one more dimension. That is to say, in 3 space-time dimensions. And in particular, it's Einstein gravity in 3-dimensional anti de Sitter space. And when I say that this ensemble is equal to Einstein gravity, I literally mean that. I mean that I could take the average over the space of CFTs of any observable. Okay? So here I'm imagining computing the average of the partition function of the surface, partition function of the CFT evaluated on some surface. And my claim is that this is equal to the action of Einstein gravity, okay? And it's going to be the action of Einstein gravity in some 3-dimensional geometry. So in the present case, if I have a two-dimensional surface that my CFT lives on, the three-dimensional theory of gravity to which it corresponds is going to be some universe, some manifold, where I fill in this geometry. Okay, so the CFT will live at the boundary of my anti-de Sitter space. So here I've drawn a two-dimensional surface, one with genus 2, and here I'm drawing a three-manifold that fills in that genus 2 surface. Okay, so this is the solid, we call it a handle body topologically, but it's some solid three-manifold whose boundary is that Riemann surface. And I've indicated it by telling you which cycles in the boundary are getting filled in here. That solid manifold is a solution of Einstein gravity with a negative cosmological constant. So it's not ADS3, but it's a solution of Einstein's equations with a negative cosmological constant. We call this Einstein gravity in ADS3 because the maximally symmetric solution is ADS3, but of course it has many other solutions. It has black holes, it has cosmologies, it has all kinds of things. It has wormholes, and this is an example of this phenomenon. Okay, so the statement is that this solution of the conformal bootstrap problem is Einstein gravity in the sense that when we average over this ensemble of any CFT observable, I get an appropriate solution, the action of some appropriate solution of general relativity. Yes.
Well, initial 2D surface is actually, say, R2. And then how do we give the
Good. So let me answer that in more detail later. But let me just say that implicitly, when I say Einstein gravity in ADS3, what do I mean? I mean the action of general relativity with a negative cosmological constant with appropriate boundary conditions. You know, part of the definition of any theory, not just a theory of gravity, is some set of boundary conditions obeyed by the fields at infinity. In the present case, the boundary conditions are that the theory look like anti-de Sitter space out at infinity in some appropriate sense. Okay, good. And that would, so I'll talk about that in a little bit more detail, but that's basically the answer to your question. The statement is that this works for every observable that we know how to compute. Okay, any observable whose Einstein action I know how to compute, or any mathematician that I know of knows how to compute, is reproduced by the CFT ensemble in this sense. Okay. We'll talk about a few examples. Well, no, I mean, I won't, it's not supposed to be obvious.
Okay.
It requires a long calculation. I won't do the long calculation, but I will talk about the long calculation. Okay, great. There are some cases where one can do this calculation in gory detail. There are other cases where, although neither can be computed explicitly, one can show that they agree. We'll talk about that for as long as you like. Okay, great, good. Okay, and so
So why do you have the average on the left-hand side?
this is a conformal field theory quantity where I'm averaging over a space of CFTs, by which I mean I'm averaging over that data that defines the conformal field theory. And this is equal to the action of a theory, okay, which is general relativity. Good, that's right. So the traditional view of the ADS-CFT correspondence is that a conformal field theory is dual to a theory of gravity in anti-de Sitter space, in the sense that their Hamiltonians agree, their Hilbert spaces agree, all that stuff. This is a somewhat different way of thinking about ADS-CFT. And the way that I think about it is that the theory of Einstein gravity is not a UV complete theory of gravity in ADS. A UV complete theory of gravity in ADS is dual to an individual conformal field theory. Einstein gravity is the thing that emerges at low energies. And so that is dual to the ensemble average over many CFTs. So for those coming from a condensed matter background, this is the way that I think about it. In the same way that an actual spin glass is a system with a Hamiltonian and a Hilbert space, you know, that's a UV complete theory, it's a quantum mechanical theory and so forth. But the way that we describe it effectively is by treating those as random variables. And when we do so, we're not talking about a particular Hamiltonian and Hilbert space. We're talking about an ensemble average of many of these. And this is described by a much simpler theory, one that we can study using, replica techniques or whatever. And my claim is that general relativity is the analog of such a theory in the study of conformal field theories. It's the ensemble averaged theory, much like we would use when we study a spin glass, treating the coupling constants as random. Is that the...
It's a kind of working hypothesis for you. You really don't know.
Okay, I mean, I have proven that the Einstein action is equal to this ensemble average. Okay, so we can. So there's a great.
Anticipating the result of your thought.
Yeah, well, there's a great deal of evidence for this that we can discuss. Some of the evidence I'll present in my talk. Some of the other evidence I won't present, but I'm happy to talk about afterwards.
Dependent on the choice of the distribution that you use for, because I guess
Great.
you do something.
I will choose a distribution, and I will explain why it is the right distribution. Yes, there's a particular distribution that I am using here.
And sorry, I have a question.
Yeah.
If you invoke the RDSFP correspondence in the way
Mhm.
I was saying,
Yeah.
this would allow you to go beyond the identity, or
Right. So, good. So the way that I think about it is the following. A UV complete theory of quantum gravity is a quantum mechanical system with a Hamiltonian and a Hilbert space. That theory is not general relativity, but it looks like general relativity at low energies. So general relativity is the thing that arises when you throw out all of the fancy UV degrees of freedom, string theory, whatever, okay? And the analog on the CFT side of throwing out those fancy UV degrees of freedom is, instead of working with an individual solution of the conformal bootstrap, that is to say a CFT, we work with this ensemble of solutions with this particular probability distribution. And I'll describe to you what this probability distribution is. I'll motivate it, and I'll explain why, from a couple of different points of view, depending on how much time we have, it's the right thing to think about when we talk about gravity. Great. Good. I love all these questions. Please ask more. Okay. So that was the advertisement where, I know how these things go. So I told you the result at the very beginning so that, you'll know where I'm coming from. So I'll start by talking a little bit more about three-dimensional gravity as a conformal field theory and how it relates to conformal field theory. I'll talk about random conformal field theories and what this has to do with the sum over geometries. And then depending on how much time we have, we'll talk about wormholes and what they mean. And we'll make contact with sort of previous thoughts about the subject. Great. Okay. I don't know what time scale am I working with?
You have about 15
Awesome.
5
Okay.
minutes per bullet.
Perfect. Perfect. So, okay. So the basic idea is that a 2D CFT is dual to a theory of gravity in ADS3. So the picture that you should have in your head is that ADS3 is the solid cylinder. It has 3 coordinates: a radial coordinate, a time coordinate, and an angular coordinate that I called phi here, but I guess I drew as x here. The constant time slices are these disks here. And the conformal field theory, you should think of as living on the boundary of this cylinder. And there's one sort of key feature of this correspondence. There's one key feature of gravity in ADS that I want you to understand, which is that gravity in ADS is just like gravity in a box of finite size, okay? So when I say ADS gravity, I mean gravity with a negative cosmological constant. The cosmological constant has dimensions of 1 over length squared. So that means that there's a typical length scale when we study gravity in ADS. And the only fact that you need to know is that gravity in ADS is just like gravity in a box of that size. What does that mean? If you're studying gravity in a box, if you study states at low energy, then they're just perturbative particles, okay? There's stuff bouncing around in that box. But the key feature of gravity, the defining feature of gravity, is that if you have a box of finite size and you start stuffing energy into it, eventually it collapses into a black hole. Okay. So what does that mean? That means that the high energy states in that theory are going to be black holes. Okay. So gravity in ADS is a theory where the low energy states are perturbative particles, the high energy states are black holes. What does this mean in the CFT language? Well, a state in the CFT is dual to a state in ADS. So that means that the light operators in the theory, the light states in the CFT, are dual to perturbative things in ADS, and the heavy operators are dual to black holes. And there's a characteristic energy scale at which things collapse into black holes in ADS, which is the size of the box evaluated in units of Newton's constant. Okay. So in the CFT language, we identify that dimensionless ratio with the central charge. It's the thing that plays the role of 1 over h bar in my theory of gravity. You know, if I restored my factors of h bar in that formula. And the point is that when the dimension of an operator is larger than some critical value, turns out to be c over 24, the operator is interpreted as dual to a black hole, you know, creates a state which is a black hole in our theory of gravity. And when it's less than c over 24, it's viewed as some sort of particle rather than a black hole. Now start going ahead and mapping things that we know about CFTs into things that we would believe about theories of gravity. Okay. So the sort of starting point is Cardy's formula, now 30 years old, for the asymptotic density of states in any two-dimensional conformal field theory. So this is the formula for the high energy density of states in a two-dimensional conformal field theory. It depends on the central charge and on the dimension of the operator that we're looking at. And the high energy density of states, it turns out, if you compare it to your semi-classical gravity dictionary, exactly equals the Bekenstein-Hawking formula. Okay. So this is, oh, sorry. So
This is for h bigger than c over 24?
This is for h bigger than c over 24, yes. So there's no, so in particular, Cardy's formula, as it was derived by Cardy, only applies when h is much bigger than c over 24. A semi-classical theory of gravity is going to be one where this formula holds for h down to c over 24, because that was the exact threshold where states collapse into black holes. Okay, so in fact, that's a very important point, which is that this Cardy's formula is true in any CFT. It's just a consequence of the conformal invariance, what we would call modular invariance on the torus. It's true in any CFT. It's true in any CFT when h is much larger than c. Einstein gravity is going to be a theory where it's true that when h is of order c. So I need to talk. Yeah. So when I talk about CFT in a gravitational language, I mean, c is much larger than 1, and I need to talk about operators h whose dimension generally is going to be of order c in order for them to have a gravitational back reaction on my geometry. Yeah. So I really, strictly speaking, I would think about a family of conformal field theories labeled by central charge, where I scale the dimensions of the operators in some way with the central charge. It turns out that there's a similar asymptotic formula for the OPE coefficients. It's a much more complicated formula, somewhat more complicated formula than this Cardy formula. We wrote it down a couple of years ago. Roughly speaking, the derivation of this formula comes from crossing symmetry. So remember, crossing symmetry was some statement about OPE coefficients. And the idea is that if you look at the contribution of the identity operator in one channel, that has to be reproduced by the contribution of heavy states in the other channel. That's also how Cardy derived his formula, but this is just done for a more sophisticated set of observables. And it gives you an asymptotic formula for the behavior of these OPE coefficients. This is also true in any conformal field theory. When we talk about a conformal field theory dual to gravity, however, as we mentioned earlier, these should hold not just for very heavy operators, but also for operators with dimension of order the central charge, two-dimensional conformal field theory. Sort of algebra plays a role. It doesn't play as big a role as you might think. In higher dimensional conformal field theories, there's an analog of the Cardy formula, but this coefficient here is unknown, right? It's, dimensional analysis fixes the high energy density of states of any conformal field theory. It says that the number of states at high energy goes like e to the d minus 1 over d at high energy times some unknown coefficient. Yeah. So the magic of two-dimensional CFTs is that the coefficient in front of this, the coefficient in front of e to the 1/2 in the high energy density of states is the same as the conformal anomaly coefficient that appears in the stress tensor 2-point function, or in the Casimir energy on the circle, or in the action on a curved manifold. So the magic thing is that in 2 dimensions, all those different conformal anomalies are the same thing. In higher dimensions, they could be different numbers. So there's one problem, okay, if we want to try and understand a CFT dual to general relativity. The first problem is that we want these formulas to hold for dimensions of order C rather than dimensions that are larger than C. So that's problem number one. And then there's a second problem, which is that there's pretty good evidence that semi-classical gravity can't be dual to an individual CFT. And the reason is because of wormhole geometries. Okay? So what is a wormhole? Here I'm talking about a Euclidean wormhole, which is a connected geometry. And in 3D gravity, it's a solution to the equations of motion, which has multiple boundaries in Euclidean signature. Okay, so these are solutions to the equations of motion with multiple boundaries. And what this means is that if you were to do a gravitational calculation of the partition function of the theory on the union of those two surfaces, it wouldn't factorize. And that just doesn't happen in quantum field theory. If I have, if I have a quantum field theory of some fields that live on some surface, and if that surface is disconnected, you'll just get the product of the integral over fields on one surface times the integral over fields on the other surface. So these Euclidean wormholes were known about for a long time, and nobody quite knew what to do with them until we arrived at the following interpretation. And the interpretation is that if you have a theory of gravity with wormholes, it shouldn't be dual to a particular conformal field theory, but an average over many CFTs. We're imagining a sum over the space of conformal field theories with some probability distribution. So for example, what is the interpretation of this Euclidean wormhole? Well, you interpret it as the variance of that probability distribution.
Look at this feature. You said that the two geometry are joint, it's joint union. So what is this in?
So here I'm imagining doing a gravitational calculation of the partition function on 2 copies of this Riemann surface. And when I compute it in gravity, there's going to be one contribution, which is going to be like the exponential of the action. So the gravitational calculation of this partition function would involve a sum over the geometries whose boundary is this union of surfaces. So one geometry that you could construct is one where the two surfaces are still disconnected in the ball, something that fills in this surface. Yeah, so you'll get like, yeah, so you'll get one contribution that looks like that. And then another contribution interpolates between the two, which would be this wormhole. Got 2 of these, right? Because it'll be the union of 2 of those. And what is this? So we would interpret this as the expectation, the square of the expectation value on one of these surfaces. And so the difference between the expectation value of the square and the square of the expectation value is the variance. That's what this formula is saying. So the way that we think about, so the fact that there are these solutions of general relativity with multiple boundaries is a puzzle. And the resolution of that puzzle is that the theory of gravity that has these wormhole solutions is dual not to a quantum mechanics system, but to an average of many quantum mechanics systems. And these wormholes are computing variances. Wormholes with 2 boundaries compute variances. Wormholes with
These not could be ABS. This is a kind of different geometry.
This is these geometries are locally ADS. They are so when I talk about ADS CFT in Euclidean signature, what I really mean is that I'm studying gravity with a negative cosmological constant with asymptotically ADS boundary conditions, in the sense that my boundary can be any geometry with an insertion of sources with any conformal structure, whose solution is a locally ADS, or is some solution of the equations of general relativity with a negative cosmological constant in the bulk. So this is something that we do study in the framework of ADS CFT all the time. Okay, so what is the ensemble dual to general relativity? Well, I almost wrote down the answer for you. So it'll be a theory with a vacuum state, dual to empty ADS, some light states that could be dual to particles, but instead of having a discrete spectrum of heavy states, it's going to have a Carty spectrum of heavy states. And the OPE coefficients are going to be random variables. And our universal asymptotic formula that I derived using crossing over here was an asymptotic formula for the square of the OPE. What I'm going to do is take my coupling constants of the theory to be Gaussian random variables with zero mean and with a variance that's given by my universal formula. I won't prove it to you, but it's actually rather straightforward to see that this actually is a solution of crossing symmetry at large central charge. In some sense, that in part follows from the way that I derived it. I mean, I derived those formulas using crossing symmetry. Those formulas were originally derived and shown to hold with dimensions large compared to the central charge. But now what one can show is that if you just look at this ensemble of CFT data and you impose these conditions for dimensions down to C/24, which is the black hole threshold, this is an exact solution of crossing symmetry up to terms that are exponentially suppressed, of order e to the minus c. Question?
Now, this one,
Mhm.
the conditions you have for your C's, can it be related to some condition on the type of disorder it would? Or did you say that halfway out of bound?
What do you mean by condition on disorder? I get,
Well, I mean,
yeah.
different ways, I mean,
Yeah.
I don't understand the word, what is he saying, to be details, I'm just guessing,
Mhm.
but if I would like to do a simulation, and I would like to get all this stuff, and I would have to put disorder.
Yeah, absolutely, absolutely.
So
Yeah.
the question is many ways of putting
Mhm.
distribution of the order, etc.
Mhm.
So the question
Yeah.
is, if I want to have a chance of getting what you're getting.
Yeah.
Would I have to put some special conditions on that disorder?
Well, so for example, the distribution of OPE coefficients is a Gaussian distribution, but it's a Gaussian distribution with a specified variant. This is a known function. So for example, if you study Liouville theory, this C0 is very closely related to what's known as the DOZZ formula, which is the formula for the OPE coefficients of Liouville theory, right? So this is not some random function. I didn't write it down for you because it's horrible, right? But this is a specified variance, okay? And indeed, I mentioned that this solves crossing only up to terms that are exponentially small. Those exponentially small terms give non-Gaussian corrections to the distribution of OPE coefficients. So although for simplicity, I didn't write them down, there also is a 3-point function, a 4-point function, and so on and so forth. There's an infinite set of terms, all of which are uniquely specified, but all of which are very small compared to these terms. Yeah. But of course, there's a relationship. Yeah. But in self-averaging theories, those are often, interchangeable concepts, right? So, I mean, if you ask me what I actually believe, I believe that you should be able to find one chaotic theory, one chaotic conformal field theory at large central charge. And if it's self-averaging, then it should be essentially indistinguishable from this theory up to some very fine-grained structure. Yeah.
So the condition that's the average of C1 through 3 is 0.
Mhm.
We have other conditions when you have two identical primaries, because obviously.
Yeah. This is
0, but
yeah. For this, I didn't want to fill this slide with too many details, but obviously C1 identity has to be 1. Okay, C identity has to be 1, and so on and so forth.
can you always normalize?
So good. Okay.
If you make
So,
composite operators out of
yeah. So, I mean, okay. The theory that I'm studying is a compact conformal field theory with normalizable states, okay? It has a continuous spectrum because it's an ensemble of such theories, but every individual theory in this ensemble is compact. The states are normalizable. You can normalize everything so that the 2-point function is equal to 1. Yeah, this is not Liouville theory. Right? I mean, Liouville theory is the CFT where you don't have a normalizable identity operator. You have to plane wave normalize your states and so on and so forth. None of that we need to worry about here.
So this should I interpret it as only one theory about C, or there are many theories that perhaps you can specify?
There are many theories, many theories, but they differ only by very small corrections. Yeah, that's right. Good. Okay. And what is this? The calculation that I won't do for you, but which we can talk about, is that if you compute, sorry, somehow my overlines became expectation values. This is supposed to be the overline average. I've replaced all my, I previously wrote averages using left and right brackets and then realized that was confusing because I had correlators. So this is supposed to be an average over the space of CFTs. If I have one boundary, then I get the Einstein action of some 3 manifold. But the thing that's cool is now that if I have multiple boundaries, so if I take the average of the square of a partition function, I get exactly the Einstein action of this guy and the Einstein action of some wormhole. Okay. How does that work? Well, let's just talk very quickly about how you might do that calculation. Well, how would you calculate the genus 2 partition function of some CFT? Well, what is a genus 2 surface? A genus 2 surface is a sphere glued together by 3 tubes. Okay? And that's a genus 2 surface. And so what do you get? You get a 3-point function on a sphere times a 3-point function on a sphere. Okay, that's a square of OPE coefficients. So a genus 2 surface has a partition function that's a sum of squares of OPE coefficients. That's basically how it works. So now, if you wanted to compute the average of the square of a genus 2, or the average of the product of 2 genus 2 partition functions, you would be looking at the average of some 4-point function of the OPE coefficients. But now I told you these are Gaussian random variables. So when you compute this average, you need to sum over the different Wick contractions between these random variables. Okay? There's one Wick contraction where these OPE coefficients contract with each other, and these contract with each other. That gives you this guy. Okay? But there's another Wick contraction where an OPE here Wick contracts with an OPE here. And the same thing for the other OPEs. That gives you this wormhole.
But in this way, you could also be quenched average instead of doing the anneal average.
Yeah, these are, okay, good. In principle, I could give you the average of the log of the partition function. In practice, I'm not powerful enough to do that because as in any other case, random matrix theory or spin glasses or whatever, quenched free energies are much harder to compute than annealed free energies. In principle, the way that I would do that is using a replica trick where I would compute the nth power and analytically continue. In practice, that's a hard thing to do, and I don't have anything intelligent to say about it, although it's something we tried, of course. Yeah, there are things one can say, but I won't say them. And then, I won't go through any details, but this works in every example where I know how to compute these Einstein actions. Okay. And it actually works not just at the level of classical Einstein actions, but also at the level of loop corrections as well. Loop corrections in general relativity and ADS are not things that you can compute explicitly in the sense that I can write down a simple formula, but one can study them and show that they agree on both sides. So what I mean by loop corrections, remember that the central charge is the ADS radius in Planck units. Goes like 1 over h bar. So loop corrections mean that when I compute one of these actions, the action of gravity in the background of some 3 manifold, or I should say the action of gravity is going to be a classical Einstein action, a 1 loop correction, and so on and so forth. And this is an expansion in powers of 1 over c. Okay? It's a loop expansion, just like in any other quantum field theory. And I'm saying that we can compute these terms in the loop expansion. The one loop terms are relatively easy compared to the higher loop terms, and they all agree. Did that answer your question? The large
CFT side, so
yeah.
what do you do to really
Good.
one versus correction? Do you modify the assumptions, or you just
Good.
with the same assumptions?
In the 1 over C, it turns out, so this Carty formula is exact in central charge. It's not valid just at large central charge, but it's exact. Good.
Large. Well, okay.
It's when
H is large.
Yeah.
compared to C, yeah.
when H is large compared to C, but any finite value of C, it's exact. Okay. Similarly, this asymptotic formula for OPE coefficients is exact in C. H has to be large compared to C, but it's exact.
But here you're assuming that H goes from 0 to 24 onwards. Do you keep that in your loop correction?
Yeah.
But
Absolutely.
eventually, all CFTs don't have this distribution.
Actually,
to C or 24. Right?
one has to be a little careful. So for example, like take the Ising model, right? The Ising model obeys Carty's formula, but the states that make up Carty's formula in the case of the Ising model are descendant states, not primary states. So one has to be a little careful. Okay. Just say that these formulas are exact in C. You have to take H larger than C, but they're exact in C. And so you could study them in an expansion in powers of 1 over C and show that they match what you get in general relativity. Math Institute. So I'll mention that the calculation of these Einstein actions is very non-trivial. In simple cases, we can write out exact analytic formulas. In other cases, like where the geometries of the surfaces are different on both sides, like if this surface has a different shape from this surface, I'm not computing a variance, but covariance. Okay, a covariance over an infinite dimensional space. We can't write down a simple analytic formula for that, but you can show that these two things are equal. This is morally speaking what the mathematicians Takhtajan and Théorie did in a sort of famous set of papers. Although, of course, I mean, we had to kind of cast this all in language, in a physics language, but there's a sort of mathematical set of calculations that I think, in some sense, we're showing these sets of results. Okay, I'm going to skip everything I had to say about wormholes, except maybe to say that the idea that Euclidean wormholes are important and have something to do with disorder has a long history, a long and interesting history. I think going back to Sidney Coleman and also some work of Giddings and Strominger, roughly speaking, is that in any theory of gravity that contains Euclidean wormholes, the coupling constants in your low energy effective theory are random variables. In our theory of nature with the standard model, if there are Euclidean wormholes, then the coupling constants of the standard model are random variables. Okay. And the sorts of wormholes that I described earlier, where you just connect two boundaries or 2 points in space-time, would mean you have a Gaussian distribution of couplings. And these theories of gravity are actually the first completely explicit realization of this, where you can write down exactly the classical wormholes that would contribute and interpret them in terms of Gaussian random couplings in the low energy effective field theory. So I think this is an interesting comment. I think it's a bit of an aside that maybe I'll discuss afterwards if people are interested. I'll just close with 2 sets of lessons. So the lesson for conformal field theories is that classifying conformal field theories is hard, but we can still find ensembles that solve the bootstrap conditions on average. And the sort of key feature is that semi-classical gravity captures some of the universal features of conformal field theories. Roughly speaking, this involves the physics of heavy operators in CFT being described by the physics of black holes in ADS. And in terms of the lessons for gravity, these are actually things that I think I've already discussed during the questions. But roughly speaking, these ensembles emerge when we approximate some sort of fancy UV complete theory of gravity by some relatively simple gravitational path integral. This picture in the back of my head really only works if we invoke ideas of self-averaging and quantum chaos. And the characteristic feature of this averaging is the existence of a Euclidean wormhole, which has to do with the presence of random couplings in some low energy effective theory. Okay, I'll stop here. Thank you. Thank you for the questions. Sorry for going over.
So I think you have two assumptions: the continuous spectrum and continuous varying conformal data from one CFT to another CFT. But I think those two properties only follow maybe at very high energy.
That's yeah. I mean, good. So no, it's crucial that when I said this solves crossing at large central charge up to some exponentially small corrections. So, for example, in a conformal field theory, the spectrum of operators is discrete, right? That is the spectrum of states on the circle, which is what I'm talking about in this language, is discrete. Okay, the spectrum is not continuous. Okay, but the spacing between those states is of order e to the minus c, because that's the entropy. That's the entropy at high. The entropy for operators of dimension of order c is of order c. So this continuous density of states is only for heavy operators.
Like no matter what C is, like C can be very large, but the lower levels are all always
good. Absolutely. Let me draw a picture of the spectrum state. You have some discrete spectrum of light stuff. You hit the black hole threshold, and then you have a continuum. And this is the place where the density of states becomes of order e to the c. And so when I say this solves crossing up to exponentially small corrections, one of the things that means is that I get to replace that discretuum by a continuum. And I'm only making an exponentially small mistake. Good, great question. Yeah. Similar, yeah, okay. Oh, stop there. Yeah, good. But you had another question or? Okay, great.
What if you choose another?
Yeah, I mean, okay, we could come back to a question that was asked at the very beginning. Okay, so I assume Virasoro symmetry here. When I talk about this density of states, I'm really talking about the density. I didn't say it. I was talking about the density of Virasoro primaries. We could talk about other chiral algebras. You could add U1 currents. You could add W algebras. You could add supersymmetry. All of these would give you slightly different variants on this kind of ensemble. I think probably what you're really getting at, though, is what if I stuck with the Virasoro algebra and just like changed the variance, say. And I don't have much to say except that this would not generally be a solution of Bootstrap conditions unless you did something like, I had to add a finite list of light states. I could add some infinite list of height states that changes the structure of the theory in some way that in a dual channel that would be reflected by a different distribution of OPE coefficients. That's a hard thing to do. Yeah, it would be a very difficult thing to do. I'm not saying it's impossible, but it would be a difficult thing to do. To some extent, I'm not trying to claim, I'm certainly not claiming that I have solved the conformal bootstrap. I haven't given you a list of solutions of the bootstrap equations. In some sense, by writing down this average solution, I'm writing what I claim would be the generic solution of the conformal bootstrap. At the very least, the generic solution of the conformal bootstrap, if we had only a finite list of states below this black hole threshold.
Yeah, this is again a very, general question, but CFT in a way are very special quantum theory. So, the direct question I would have is, I guess the answer is probably technical, but would it be possible to define a gravity which is equal to a QFT, which doesn't have a conformal values?
People certainly, ADS CFT has been around for 25 years at this point. People certainly spend a lot of time thinking about what theories of gravity might be dual to theories that contain some dimensionful scale. There's a lot that we can say, very little of it precise. I think it's an interesting territory for future exploration. One problem from my point of view is that, for me, the problem with the classification of CFTs has been reduced to a mathematics problem. I know the data, I know the constraints on that data. I may not be able to solve it, but at least it's a completely well-defined system. When we're talking about the classification of general quantum field theories, it's a much more difficult subject, and it's not quite at that status. Many people have talked about holographic tools to QCD, to large Yang mills, to condensed matter systems with dimensional scales and so forth. There's a ton that can be said, but I don't have anything particularly useful to say from this point of view.
Going back to her question, I mean, I think that the representative of the best representative of your ensemble average probability is in some sort of semi-classical description of a conformal theory. So
Semi-classical in the sense of large central charge.
You don't have access to the lower line state that would be discrete.
That's right.
You don't have a good picture of
It's like a kind of unattended.
Yes.
But the low energy cases which is reach, but then when you work on
Yes. Yes.
Well, I mean, to some extent, when I say that I solve crossing, I have both a vacuum state, which is important at low temperatures, and I have a density of heavy states, which is important at high temperatures. The reason this ensemble is crossing invariant is that I have both simultaneously, right? At high temperatures, this is like, if I were only studying at high temperatures, I wouldn't care about the vacuum state. If I were only studying at low temperatures, I wouldn't care about the heavy states. I have both. Yeah, but maybe I don't know if that was, okay, I interrupted you, I think. So, or no, that was.
What it is. I mean, how about 2 + 1 means here?
It's very hard. I mean, it's very hard, right? Like, okay. Okay, I mean, you want, yeah, I mean, if you want me to make a conjecture, I'll make a conjecture. Okay. Okay, I mean, general relativity in ADS4 is dual to the maximum entropy probability distribution on the space of solutions of the CFT3 bootstrap. The problem is I can't do any calculation. I don't have.
You're saying that the number that appears in the distribution of HH bar, the C is replaced by some effective coefficient. Do we know what it is, or
Depends on the conformal field theory. There's no, like, similarly in ADS4 gravity, there's no, like, the structure of black holes is much more intricate. Like, this, like, Cardy's formula reproduces the Bekenstein-Hawking formula. Like, the fact that they agree, like, the fact that you get this 1/4 here is, like, anybody can get an entropy proportional to horizon area. That's not very hard. The thing that's amazing about Cardy's formula is it gets this factor of 1/4, right? That is the gravity version of the miraculous statement that the same conformal anomaly factor that controls the high energy density of states in Cardy's formula is the one that controls the stress tensor 2-point function or the Casimir energy on the circle, right? Like, the fact that there's only one conformal anomaly coefficient in 2D that controls everything is like the CFT version of the fact that you can get that 1/4 correctly in Cardy's formula. In the context of higher dimensional conformal field theories, the problem, I guess, is really identifying which of the possible anomaly coefficients in your higher D CFT is the one that governs this high energy density of states. There's many different possibilities. In examples of ADS CFT that we understand well in higher dimensions, there are additional coupling constants, things like 't Hooft couplings, that go from weak to strong coupling as you go from the bulk into the boundary. And so what that means is that they're very difficult to compute exactly in the boundary theory, right? Like, what you would want to do is study n = 4 Yang mills, for example, but you would want to study it at strong 't Hooft coupling. And there's this famous mysterious factors of 3/4 that appears there that when you go from weak to strong 't Hooft coupling, which would be the analog of some adjustment of that anomaly coefficient in higher dimension. All of which is to say that higher dimensional gravity is much more complicated.
if you're agnostic and you just put some coefficient that's large, like C twiddle, does the rest know that it does?
I mean, dimensional analysis tells you that the high energy density of states in some d-dimensional CFT, d+1 dimensional CFT, goes like that, right? With some numerical constant there. The problem is that I don't know a way, there's no universal formula for that numerical constant in 2D CF, in higher DCFTs. But the general form is just dimensional analysis. You do the free energy of the theory on a circle times flat space, and then you take the circle, shrink the circle.
But like, do you need that information, or can you do the averaging without it? You just use that form and.
Coefficient is the 1/4, is supposed to be the 1/4 in the Bekenstein-Hawking formula. Like, yeah.
But let's say don't take the 1/4.
Maybe let me put, yeah. I mean, people have certainly tried saying the words in higher dimensions. The question is, what can you do? Like, you can say the words. Okay, we said the words, but now what do you do?
The fact that the graviton does not exist in 2.1 gravity, but exists above, it makes a difference.
Absolutely. Yeah, no, that's crucial. So, I didn't go into the details, but of course, three-dimensional general relativity is much more like a Chern-Simons theory than a gauge theory, right? It's a theory with no local degrees of freedom. It still has degrees of freedom. It has boundary degrees of freedom. It has sort of topological degrees of freedom. Much like a Chern-Simons theory, but it has no local degrees of freedom. And of course, that is the mirror of the fact that in 2D CFTs, everything, you have this infinite dimensional symmetry algebra, and conformal anomalies fix a lot, all but like order 1 parts of the structure of the theory. So for example, analogs of Cardy's formula in higher dimension, but they're just not generic. Like this numerical coefficient isn't fixed. There are formulas for OPE coefficients, asymptotic formulas for OPE coefficients in higher dimensions, but they're, they depend on the details of the theory, not just the central charge. I mean, one thing that I didn't emphasize, but this universal formula for OPE coefficients depends only on the central charge, not on any other details of the theory. Whereas in higher dimensional CFTs, it would depend on lots of other things like the OPE coefficients of the theory at low energies and stuff like that. I mean, one can, which isn't to say one can't write papers about it, right? One being me, right? But like, there's much less that one can say explicitly.